I think today it's a great day for science. We find an agreement between all 6 parties that the site of the Iter, that's the fusion building, will be in South France in Cadarache. I think it's a very important agreement. It's important that we reached it with all 6 parties in an international environment, because this is somehow setting a course also for the future, how the cooperation on the scientific field should be done in the cases like this and also broader.
During this century, the world's population will double. From 6 billion people today, it will rise to 10 billion by 2050. More importantly, on average, we will be using a lot more energy in the world than we do today. Energy consumption will probably be about 2 times higher by the middle of the century, with an even stronger increase in electricity consumption. To meet the future demand, combustion of fossil fuels may well be used increasingly, with, as we already know, dramatic consequences on the climate due to emissions of carbon dioxide and other greenhouse gases. As this table shows, oil, gas and coal are the most commonly used sources of energy at present. Under these circumstances, developing and improving new, sustainable and renewable sources of energy is therefore crucial for the future. 50 years ago, nuclear fission power plants were developed which presently contribute about 35% to European electricity production. Today, solutions for the waste issue of nuclear fission are being investigated, and new and renewable energy sources are being developed. All sources of energy for the 3rd millennium must take account of environmental requirements, operational safety and availability of resources. All European member states and countries associated with the Euratom fusion program are well aware of this. Indeed, Europe has become the world leader in research on a new sustainable source of environmentally benign energy that does not emit any greenhouse gases: fusion. Fusion is the sun's source of energy. The heat and light we receive on Earth originate from these fusion reactions. Part of the energy produced remains inside the sun and generates a temperature of 10 million degrees Celsius. This very high temperature, coupled with the gravitational forces and the density of the sun, causes fusion. Under these conditions, hydrogen atoms become separated into their fundamental components, electrons and nuclei, which are then independent of each other and form a new state of matter called plasma. Finally, the nuclei fuse, producing helium and giving off energy. Today, scientists can reproduce this process on Earth. The nuclear fusion process refers to the merger of 2 light nuclei, hydrogen and hydrogen. This gives an atom of helium. But the 2 hydrogen nuclei have a positive charge. They don't want to merge. So, we force them. When they're very close to each other, they fuse, and this gives off an enormous amount of energy. How can we force fusion of 2 nuclei? By using a device to attempt to reproduce conditions in the sun. This is not easy. In the sun, this process requires a temperature of 10 million degrees Celsius. If we were to try to achieve it on the Earth, it would need 150 million degrees Celsius. So how do we do it? I'll show you. We take a glass tube with gas in it and we heat it in a special microwave oven. This is the first essential step to achieve fusion on Earth, heating the gas to a very high temperature by means of an external supply of energy so that it becomes a plasma. I showed you that with a microwave oven, I could heat the gas until the atoms split and become charged particles that consequently emit light. But we cannot reach very high temperatures by this means, because the particles touch the side of the test tube and cool down. So we must develop a system to keep them from touching the tube. To do that, we have another experiment using a magnetic field to attract the plasma and prevent it from touching the tube. So this is the second indispensable step, preventing the plasma from dispersing and cooling. In the sun, this tendency is counterbalanced by the force of gravity. On Earth, confinement by gravity is impossible, so the solution is magnetic confinement. We can confine the plasma. But how can we maintain an enormous quantity of plasma in a reactor? Can we really make it float using a magnetic field?
Oké, ik zal u laten zien dat het inderdaad mogelijk is.
The answer is yes.
Materie op te hangen in de lucht,
We can suspend it in the air,
in contact is.
where it does not touch anything at all.
Dit doen we ook in een reactor.
This
alleen
too we
dan
do in a
plasma,
reactor, but the tool is plasma.
dus niet met de
And since the plasma does not touch the sides, we can heat it very, very hot. In a reactor, the plasma is confined in a very stable way in a donut shape called a torus. You may think this shape is a strange one, but it's one of the shapes accepted in nature. Let me demonstrate with this box that blows smoke rings when I tap the back. This smoke ring shows how the toroidal shape can be propagated through space without any exchange with the environment. We use the same principle in a fusion reactor. A torus is a very stable shape. If plasma is confined to this shape, we can maintain the heat with no loss to the exterior. On combining all these principles, a fusion device looks like this. This is what is called a tokamak, and this is the inside of the device. But having a device isn't enough. It needs fuel too. The two elements most susceptible to fusion on Earth are deuterium and tritium, two hydrogen isotopes. Tritium is generated in the device itself using lithium, which is abundant in the Earth's crust. Deuterium is generously present in seawater. In other words, these two resources are practically inexhaustible. This is the first advantage of fusion.
Fusion would really help achieve security of energy supply in Europe. The resources which are required, the fuel, if you like, for a future fusion power plant, the fuel is available everywhere. And so we would not be dependent on shipments of raw materials or fuels for future fusion power plants.
Other significant advantages are the fact that the fusion of the two isotopes we see here in plasma form does not result in emitting any gases with a greenhouse effect, that chain reactions and related possible accidents are excluded, and that long-term radioactivity will be very limited.
Dus de brandstof voor een fusiecentrale
The fuel to operate a fusion power plant consists of hydrogen and lithium.
zijn beide niet radioactief.
Neither of these is
Uit de
radioactive.
reactie komt is
The reaction gives helium, which is not radioactive either.
in de reactie.
But during the reaction, tritium is formed in an intermediary stage.
Als alle
Tritium is radioactive, but if all the tritium in the reactor were to suddenly fly out the chimney, we would not need to evacuate the immediate area. The risk is relatively small.
klein risico. De binnenkant
The inside of the reactor becomes radioactive during energy production. As years go by, the inner surfacing must be replaced from time to time. These plates from the inner wall must be stored before they can be reprocessed. This is activated steel, whose radioactivity decreases over a period of 50 to 100 years, down to a level that is lower than the ashes from a coal power plant.
as van een kolencentrale.
So this is really very low.
Dat is werkelijk erg laag.
Now let's have a look at a concrete example. Europe, the world leader in this field, has already undertaken several research and development projects dealing with fusion. Among these, the JET project for Joint European Torus, which is the largest tokamak experiment in the world. It was constructed between 1978 and 1983 in Culham, United Kingdom. Since then, its exploitation was and still is focused on understanding and developing powerful high-performance fusion plasmas as the further step towards fusion power. In 1991, JET was the first project in the world to achieve a significant amount of controlled fusion power, 2 megawatts, with deuterium and tritium. This result was an important event, because it has shown that fusion energy could be produced on Earth. JET has increased this power to 16 megawatts, a world record still unbeaten today. This result paves the way for a larger experimental project like Iter. There were also two very important byproducts. On the one hand, safe tritium handling, and on the other, successful remote maintenance of the tokamak. Iter, that's the key word. It means the way in Latin. It is the road to fusion energy, a unique project embracing the European Union, Russia, Japan, the Republic of Korea, China, and the United States. Now a consensus has been reached at international level, and the final choice for the construction site is Cadarache, France. The objective of Iter will be to prove scientifically and technologically that fusion can be tamed as a source of energy. Here is the model of the future Iter experiment facility. Iter will be constructed using the results of JET, with the same concepts and the same toroidal shape, but on a much larger scale. The plasma volume of JET measures 100 cubic meters. Iter will be 800 cubic meters. Why so? To use as little outside energy as possible to heat the plasma. In the case of JET, the size is such that losses are compensated by a source of outside energy. The new feature of Iter is that the internal source of energy resulting from the fusion reactions will compensate losses, so Iter will not depend exclusively on power supplied from the outside. This is possible by increasing the size of the device. The larger the plasma, the easier it is to maintain the high temperatures required for fusion. In Iter, we estimate that we can control the process by supplying power of about 40 megawatts, whereas the fusion should produce 400 megawatts of power. It's possible that we will be able to increase this ratio to about 30 to 1 for a reactor producing electricity. The Iter project will be implemented over about 35 years, including the construction, exploitation and deactivation of the facility. The construction of Iter in Cadarache, which will last about 10 years, is planned to start before the end of 2005. Following Iter construction, scientists and engineers from all over the world will commence the exploitation of the experiment, including tests related to the large-scale production of energy by means of fusion. Until recently, it was considered that the first kilowatt of electricity to be generated by a demonstration-type fusion plant could be supplied by about 2050, but it is hoped that this date could be brought forward.
Iter is an experimental device to test the technologies, put them all together. It will not be equipped with turbines to actually generate electricity. Assuming Iter works, once we understand the results, then maybe between 15 and 20 years from now, we will be ready to start building a real power station which will produce electricity. That could be operating within 30 years, a few prototypes. After that, before the middle of the century, we hope to have large-scale fusion power.
The last stage will therefore be the construction of an electricity-producing power plant that is connected to the electricity distribution network, a new source of energy for mankind, reliable, sustainable, emission-free and competitive, could then become part of our daily lives.
We are all searching for an answer to a proper energy mix of the future. We want to get a sustainable source, we want to get something which would be environmentally friendly. Fusion, it's one of the possibilities. So I think that doing that in an international environment gives us the possibility that we would get that source even for commercial use sooner. Of course, it was a lengthy and quite difficult negotiating process. All the parties which have been involved, of course, have had quite high interest of getting a positive agreement, but experiences which we've learned in this process are very positive. I think that all the sides, all the partners came out from this agreement stronger. I think that especially Japan and European Union built a very strong partnership which is built on the trust. Now we have to finalize the international agreement, so practically these are technical steps which has to be done afterwards with only one idea: to start building the site during this year, at the end of this year. Yes, I have the plan to visit it very soon. I want to gather together with the regional, local authorities, of course also with the ones who are directors who are running the business there, and to discuss about the issues which are connected with the project itself.